Hi, everyone. So welcome to our last video, or I guess our last first video, since this is our first week of unveiling videos and OCaml is the language that we've saved for last. So because it is our last video on this first week, I wanted to just take some time to announce that we're probably going to be changing things up a little bit with this video format, just because we think that these longer form videos are a bit more hard to digest than we would have liked. And also on our end, it's a bit unsustainable to kind of get everyone together and film these longer videos. So we're going to be changing that up a bit, and we'll be posting some updates about that in the coming days. Otherwise, I just wanted to dive into OCaml with you guys. And so we often think of OCaml as a more practical version of Haskell because it is a functional language that is very similar to Haskell, but it has the ability to do some more imperative things, while Haskell is a very pure functional language and doesn't have that ability. And so you might want to use those imperative features maybe for performance benefits or something like that. But OCaml is also a very beautiful functional language. And so we're going to be taking a look at that today. So what we can do is we can start an OCaml REPL. Oops. Or actually, I already have one started here. And so let's just clean it and start with a simple 1+1. So as you can see, basic operations work the same in OCaml as they do in most imperative languages. We see the proper return value. OCaml also tells us the type of that return value since it's a typed language, but we won't go super deep into types today. One interesting thing is that OCaml chooses to denote the end of a line with two double semicolons, which coming from an imperative language like C or Java or JavaScript might take a bit getting used to because those only denote the end of the line with a single semicolon. And I myself will probably make this mistake quite a few times during this video, just trying to end it with one semicolon. So we can see that other sorts of basic operations work like we'd expect. Order of operations also work like we'd expect, even though we saw yesterday in APL that wasn't the case. And so let's just do a division to get everything in there. So 1. We can also define variables in OCaml. So we always define variables with the let statement. And the reason we do that is because a single equal sign actually tests equality in OCaml, which is pretty crazy if you come from another language, because something we all learn very early on when we're learning to program is that there is sort of a difference between assignment and equality testing. Single equals, double equals. Double equals also does function as an equality test in OCaml, but sort of getting around that preconception that a single equals is going to be assignment might be another sort of thing you have to get used to. So, right, we can define variables with let. Let's define a variable y, and we can add them. And we get 150. Another interesting thing we can do with lets is build up more complicated expressions. So let's say let x equals 43 in this expression over here. I don't know what the answer to this is going to be, but it looks like it's 1,870. So that turned out kind of nicely, actually. And so if we check the value of x, though, it is still 50. Let in OCaml, like in most languages and in every language we're doing in the Paradigm Conference, only controls local scope. So in this local expression, x is 43, and we can calculate this value with it, where we say 43 times 43 plus 43 divided by 2, and we got 1,870. And actually, I just realized that the reason this came out nicely is because we probably did not use the special operation you need to do when you're using floating point numbers. So we'll get to that in a few minutes. But this is probably not actually the completely right answer to this expression because 43 divided by 2 wouldn't come out that nicely. But returning back to what we're talking about. So x is only 43 in this let block, but in the global scope of the program, it is 50. And so we should also note that this 1,870 didn't get bound to anything. It was just returned as an expression. And so if we were doing an actual program, writing some useful function, we'd actually probably want to bind this to another value. And on the note of functions, let's try some out. So we have a print string function, which we can use to say hello world. We also have a print int function, which we can use to print numbers. And we can do some more complicated expression there. So this will give us 200. So we should look for a hello world 200. Oops. Okay, let's just try one. Okay. Okay, So I think what I just showed you was a case where you actually do need parentheses to remove ambiguity from in what way the function should be evaluated. But generally, you can do this without parentheses as long as we have each specific expression clearly delineated. So for example, this throws an error because print int thinks we're calling 1 and plus and 1 as separate parameters. So in this case, we need a set of parentheses to disambiguate what we really mean and in what order we want to call the function. But in most cases, if we're just dealing with already sort of evaluated expressions like hello world, a string, then we can just not use parentheses when we're calling our function. And that's sort of something that's similar to Haskell as well. So with that out of the way, let's see how we can define our own functions. So we'll define a function square. So we always use let for functions and always use let for variables. And something you may be learning if you've looked at some of our previous language videos is that a lot of functional languages use just the same keyword to define both functions and variables, which simplifies things a lot. So let square of x. Square is the name of our function. X is the name of the argument we're taking in. And then we can just return x times x. So now we want to load our function. So how we do that is we say use main.ml, which you might see here is the name of the file we're in. And you can see it just loaded in our square function. And again, OCaml is a type language, so it realized this is a function mapping integers to integers. And we could explicitly tell OCaml that, but it's also smart enough to figure out for many functions that we define what the type signature of those functions are all by itself. So 14, we get 196. Let's do a big number just for the fun of it. And we get this result. So I should actually point this out, like I was mentioning earlier. If you try to add a floating point number like this with plus, it won't work. So you actually need to do something like this with a plus and then a dot after it. So why did that not work? I think it did not work because of this. Let's try. Okay, so I needed to indicate that both arguments were actually floating point numbers. Then we can just use plus dot to sort of print out that result. So let's try this with our print in function. Say 1 plus dot 1.0 plus dot 10 divided by 9. Okay, I guess we'll just do this. Oh, okay, well, never mind. Print int would expect an integer, of course. So that's my mistake. But you can use plus dot to add together floating point numbers. And that continues the same sort of idea for the other operators as well. So now that we've defined a basic function, we can try and define something a little bit more complicated. So let's say greater than AB. So this function takes in two parameters this time, A and B. And we want to say if A is greater than B, then we will return greater than, else less than. Let's try loading this. Okay, it loads successfully. So again, we use let to define the function name, list of arguments, equals function body. In this case, we use an if statement, which is very similar to if statements in other languages. We do use then in OCaml, like in Haskell for our if statements, then and else. And so we usually put if and then on the same line and then else on its separate line. So now we can, again, load in our file. And we can test it. 5 and 10. So 5 is not greater than 10. So we'll get it's less than. And on that note, all of the logical operators are pretty much the same in OCaml as in most other languages. There are two exceptions to that statement. So like we saw before, it's a single equals that is equality for equality testing. And then for inequality testing, instead of exclamation equals for not equals, we use this double angular bracket symbol, which sometimes means like joining two strings in other languages, I think. But in OCaml, we can see that if we pass in two different things, it will give us a true value because it is the not equals function. So we've sort of gone over most of the types in OCaml so far. You have integers, floating point numbers. You can have Booleans, true and false, which are undercase in OCaml. And you can have strings. Again, we've been using strings. So those are sort of the basic types. Now we can try and define a more interesting function, factorial function. So we actually have to specify that we want to call this function factorially with rec. And so much stuff in OCaml is factorial, so you'll actually use rec a lot. The reason we do this is, I believe, to sort of specify to the OCaml compiler that this is going to be recursive, so it can do certain things to make this more performant when we call it in a recursive way. Although I don't know myself too much about that, but you do need to specify rec for a recursive function. So let's see, we can say if n is less than or equal to 1, we want to return 1, right? Because factorial of 0 is 1 and factorial of 1 is 1. However, in any other case, we want to return n times factorial of n minus 1, right? If we have factorial of 3, that is 3 times factorial of 2, and 2 is 2 times factorial of 1, but 1 is always just factorial. 1 is just always 1. Factorial of 1 is just always 1. Okay, so again, let's load in main.ml. Let's clean up some space here as well. Okay, so let's try it. Factorial of 1, 1. Factorial of 2, 2. Factorial of 3, 6. Factorial of 5 should be 120. Tap that one. Factorial of, let's see if it can handle 14. Okay, so we got that number back. Now, this is somewhat functional code. I mean, in terms of like, is it idiomatic functional programming code? We can make it more idiomatic though with something called pattern matching. And we haven't talked about that much in Haskell yet because we went through some other stuff, but we are going to go through that in OCaml. And it's a big part of Haskell as well. So we can write it like this, although this definition is a bit opaque. It's not super clear. You have to think about it a bit. We want to try and make our code as easy to read as possible and as functional as possible without it being super hard to read. So let's say factorial 2. And we're going to use the match with sort of statement here. Okay, let's set this up. So what did I do? I created a function like normal with 1 parameter, but I now started this matching block where I'm matching n with. So this is sort of like an if statement, but an if statement, I guess this is more general than an if statement. An if statement is a specification of a match with 2 branches. A match could have as many branches as we want, and it matches against a specific value. So we already know that the specific value we're looking for in the first branch of our if is 0 or 1. So we can match against that. And then in the second branch, it's just an else, which means we don't really care what it is. So we can just put any symbol in here. We're not going to use it again. We don't care about it. That may not actually be the best explanation of pattern matching. And sorry if it isn't. I'm trying to think exactly how I first sort of felt when I saw pattern matching before. It's a pretty big shift from if statements. Again, like I said, an if statement is really just a specification of a pattern match. So it's just learning to think a little bit more generally here. And this sort of single pipe does mean the or command in OCaml. So this is 0 or 1, and this is anything, always true. So if it's 0 or 1, we know we return 1. Otherwise, we return factorial of n. So the factorial of n minus 1 times n. So again, we can see how this is really just writing the if in another form, but you have to admit it's an easier form to understand. We can sort of split everything up on its own line, and we can describe it more clearly. Actually, I realized I should have a double semicolon after there too. Okay, let's load in our file once again. Semicolon. Okay, it loaded in both of our functions now. So let's try again, factorial 14, factorial 214, and we can actually see if these functions equal each other by using our equals command. And so In terms of performance or something, there wouldn't be too much difference. Again, it's just stylistically, this is nicer and easier to understand. And we can actually go one step further to make this as idiomatic as possible in OCaml. And that is factorial 3. Removing the necessity of listing out our argument. Okay, I'm mispronouncing a lot of things. The necessity of listing out our argument explicitly. So in cases when we have functions with one argument, and this is important because this only works for a function with one argument, we can use the function keyword. This function keyword, it automatically triggers a matching block, so we don't have to say match. And it assumes we only have one parameter, so it automatically triggers a matching block with whatever parameter we give it. So we can't use function for a function with more than one parameter. But in this case, I can just copy the same code, and I just get to avoid writing match, because since this is a function of one argument, the function keyword automatically triggers this matching for me. And in this case, what we actually have to do is we have to bind this value, because before we're saying, oh, we don't care about what this is. Now we do care, because we haven't defined n as the argument. So we need to bind whatever value is coming in here as n. Okay, let's load this file one final time. Let's try and push it to 25. Doesn't break anything. I don't think it will. No. Okay, so it looked like it became too big of a number that I have to express it negatively. So let's try 22. 3. Okay, let's make something a lot lower. Okay, so there we go. And so, yeah, it's kind of cool actually to see this evolution as we slowly make this more and more functional. But that is a quick tutorial on functions. Obviously, you can have a lot more complex things going on in functions, but those are the basics. So we should also go over lists, which are OCaml's array type. So this is an empty list. So what you'll notice I did here is I separate all the elements with single semicolons. I denote the end of the line with a double semicolon. You'll also notice that, like in Haskell, this gives an error because OCaml is a typed language. It tries to assign a type to the list. And so if we put in elements of different types, it gets confused and throws an error. So we can have lists of anything, like in other languages. We can have lists of lists. So here's a sublist of integers, but again, those sublists must be of the same type. So I can't have a list of differently typed sublists. So I can't have a list where the first sublist is 1, 2, the second is 3, 4, or something like that. I can also add elements into lists. So I can do this cons operation, which is a double semicolon to sort of concatenate an element to the head of a list. I can also join a list to the head of another list with this append operation, which is represented by an @ symbol. So we have double colons and @ symbol. And now that we understand a very few amount of things about lists, let's see if we can try and create our own function to get the total of a list. So of a list of integers, can it add up to the total? And so how are we going to do that? Well, immediately your mind may leap to something like for loops from an imperative programming point of mind. But like I said, we use recursive functions for pretty much everything in OCaml, and we're going to do this recursively. So let rec total. It's going to take in a single list. So one parameter, which means we know we can use function. And now what are we going to do? Well, let's think about the different cases our list could be in. Whenever we're doing recursive functions, we want to reason about a base case or a case where we don't call recursively. So what would that be? Well, in this case, that's just the empty list. We don't have to recursively figure out what the other elements are at that point. An empty list is just going to be 0. Now, what do we do about the more complicated case? Well, we can think about splitting a list into its head and the rest of the list. And so recursively, we take out the head and add it to the same function called on the rest of the list. And then we keep calling that function again and again, and we keep extracting at the head and adding until the rest of the list is just the empty list and is 0. So how do I extract out the head? Well, we saw here that we have this operation to add in a head, a double colon, a cons, and a pattern match. What this does is it actually does the opposite sort of. It extracts out the head. So it splits up our list into its head and tail. And now what we want to do, and we're done. That's the function. It's really elegant, and it's really cool to see how we're able to package all of that logic into this very concise statement. So if it's an empty list, 0. Otherwise, split the list into its head and tail, add the head to the total of the tail. And that will keep doing this process until the tail is actually just the empty list and 0. So let's okay, so a total, this list's total should be 6, and it is. See a total of a more complicated list, maybe 1, 3, 5, 76. So that should have a total of, 85. So that's a cool way to write a recursive function to find the total of a list. Now, another thing we could try and do is find the length of a list. Okay, so let rec length, a function for length. Again, we're going to take in a single list, so we can just use function. Again, we're going to want to do the same sort of logic for the first part. If it's just an empty list, the length is 0. And how do we break this up? Let's try what we did again, split it into a head and a tail. Now this time, we don't care what the specific value of the head is, because when we care about length, any value, no matter how big or small, it's all the same. It just adds 1 to the length. So it's basically the same as before. If we don't even use head, we can just bind it to an underscore, which is more idiomatic to do. We don't have to waste creating a whole variable for that. And so now we get a length function. Length is loaded in, you can see right there. And I should note that, again, we have been generating types for these functions. So something interesting you'll see here is total has to be a list of integers because we can't add together elements that are integers. Length, on the other hand, the OCaml compiler realizes that it can be a list of anything. And so it uses this generic abstract type A to stand in for anything. So I can get the length. And the reason it can be anything is because we're not doing anything specific to some type of data type. We're doing the same logic regardless of the data type. So it can be a list of anything as long as it's a list of the same things. So a list of 2 strings gives us 2. And so we can do all sorts of cool functions like that. We can create functions to append to the end of the list. We can create functions to map other functions over lists, all using this sort of recursive paradigm. And so that's a lot of the basics of OCaml. There are some other interesting things we can do, including defining our own types and other things like that. And we probably shouldn't get into those too much, although actually I will show you a little bit what this looks like. And this can also be a sort of teaser for the stuff we'll be doing in Haskell as well. So say I wanted to create a list of a certain number of colors. Like this could be part of a larger program. So I'd have to represent those as strings because red, green, and blue don't mean anything to the language. But if you think about it, what does true or false mean really to the language? Well, they're just specifications of a Boolean type. And the same thing for any other sort of data type. So in typed languages, we can create our own specifications of a type. So we can create a type color. I don't know why it's trying to autocorrect to that. So we can create and just see that this compiles. This is a valid thing we can do. And now, let's see. I can create a list of colors. Right. So you see, it tells us the types of everything we loaded in. And these work now, even though this is a type of a different color, because look, it recognizes, first of all, and this is going to be more clear when I do this. An int list, we just defined our own type and it became a color list. So OCaml accepts our type and integrates it into everything, how it does everything. And so all of our existing functions can work on this as well. Logging out for some reason, so I'm going to have to. But I can use my length function on a list of color types now. So yeah, that's pretty cool. That's obviously just scratching the surface of what we can really do using types. And now that I think about it, I know I mentioned that I wouldn't show the map example for recursive functions, but I actually think it's really cool. So why don't we end on this? So map is a function that is a higher order function. And we've used this term a lot in a lot of our videos this week, probably every one of them, actually. Map is a higher order function. It is a function, one of whose arguments is another function itself. It takes that function and applies it to every member of a list, not Lisp. So we need two arguments here, so we can't use function. We still want to match, though, pattern match. So what are we going to pattern match? Well, we can't pattern match against the function, right? Because when we do recursions, we want to change something. We don't want to change our function. We want that to stay the same. So we can at least intuitively tell we're going to pattern match against the list. And we can also probably intuitively tell that in this case, we're always going to have a base case. And for list, that's always going to be the empty list case, essentially. Well, what do we want to do then? If we're trying to map a function across the list with no elements, then that list has no elements which we can apply the function to, so empty list. So again, it's always going to be empty list to some sort of other empty quantity, maybe a false or a none or a 0, or in this case, another empty list. Now, this is the more difficult part. So we can sort of assume we're going to want to split the list again and do a head and a tail. Now, what do we do here? Well, the head is its own distinct element at this point. So we can apply the function to it. And then you don't need parentheses. I'm just doing this to make things a little clearer. So we want to apply the function to the head of it. Now we want to join that function that this element has now been applied. The function has been applied to the element. It has been mapped over. So that element is done. The rest of the elements still need to have it be their turn to be mapped. So we can do that. But how do we take this distinct element and now put it back into the list? Well, you remember this function, I'm sure, from earlier, which is exactly the same thing we're doing when we're pattern matching, right? I mentioned how when you pattern match, oops. When you pattern match, the double colon cons operation splits apart, but when we just write it as an expression, it joins back together. So we're going to join back together this element with map over the tail. Okay, so this is a little more complicated than before, so I just want to break it down again. If we have a list with no elements, we cannot map our function over anything, so we just return an empty list. In other cases, we split into a head and a tail. We map over the head because that's its distinct element. Then we join that with map applied over the tail. And so the tail, for example, let's sort of work this out with 1, 2, 3. So we would map the function maybe +1 over 1. That becomes 2. Now we map the same +1 function over the tail, list of 2 and 3, and then we split that again into 2, the head, and then so we continue on in that fashion. And so let me run that. I am in the OCaml. Okay, I'm not. And I just want to show something quickly. So, that's not what I'd expected. Okay, wait, let's just try this for a minute. Hopefully this works. Okay, so I'm probably entering something wrong here. But you are able in OCaml to have sort of partial functions like you have in Haskell. So I'm not entering this correctly. I forget exactly what mistake I'm making, but you can sort of create partial evaluated functions. So another way we can do this is creating inline functions. So maybe just ignore what I was trying to do there. That was a mistake. Sorry about that. So this is an inline function. So it's an anonymous function. I don't bind it to a specific name. I just say this is a function that takes an x, returns x plus 1. So it's not very good for writing complicated functions, but if you want to be concise and use a function in another operation like map, we can just create it inline like this. And so you see it gets mapped over each element of this list, which is pretty cool. So we can also create larger functions. For example, our factorial function, still defined. And let's just use normal factorial so I don't have to confuse myself with the spelling. So I can map factorial across 1, 2, 3, 4, 5, 6, 7, 8, 9. And so let's make this a bit wider so we can all see that. So now I have this bigger list of the factorials of the first 10 numbers. So that's pretty cool. And let's do one final example. So now we want to get length. We're mapping length, but length only works on lists. So if we want to map it, we have to map it across a list composed of sublists. So it gets the length of each of the sublists, which is 2. So we get 2, 2. And so, yeah, that's OCaml in a nutshell. The key takeaways, it has some imperative features. We didn't go too much into that, but it does have some imperative features. It has a lot of the defining variables, basic operations, defining functions are pretty simple as you would expect. It has a few sort of strange symbols for equals and not equals then. That may be something to wrap around, as well as the double semicolon ending. The main thing you should take away is OCaml is, like Haskell, a language that is all about solving problems with recursive functions over for loops explicitly. And I think maybe OCaml even more so than Haskell a little bit. The fact that we have the specific rec keyword just shows you how important recursive functions are in OCaml. If all the functions we wrote here, 1, 2, 3, 4, 5, 6 of them were recursive functions and 1 was not recursive. And we can see the difference in the power of what we were able to do. A recursive function in 3 lines is able to map another function across the list. A non-recursive function, we were able to do this sort of trivial example. So yeah, OCaml is all about creating functions, as are all functional languages, but there is a particular focus on sort of using recursive functions to solve complex problems. And this also exists in Haskell as well, but perhaps in OCaml a bit more so. So OCaml, there's this big sort of shock with trying to figure out how to solve all these problems recursively. And I know I went through some of this sort of quick. So when I was first exposed to the OCaml for the first time as well, this was a lot to wrap your head around, especially this idea of like pattern matching within the function and then using that in recursive functions. But it allows us to build up these really cool, concise, and powerful functions. For example, this map function, super concise, super readable once you understand what it's saying, and also super powerful. So you can just imagine when we learn more than 30 minutes of OCaml, what other sort of things we might be able to do. So yeah, if you're interested in OCaml, please check back. Like I said, we're probably going to be changing up what we're doing, but we're definitely going to be continuing to release materials. Please take a look at our written curriculums, and please check out the Paradigm Conference and register and have a fun time learning and exploring with OCaml until our next video. Thank you.